A 7-story building, a bridge carrying tracks, all of it built from a material that engineers just one generation ago called the poor man's wood. Good for little more than huts. And that material is grass. Ordinary grass that grows back in less than 10 years. How is that even possible? And why is the rest of the world only now starting to pay attention? For 10,000 years, wood was humanity's primary building material. Houses, bridges, ships, everything started with timber. But wood has one serious flaw that nobody likes to say out loud. It grows too slowly. Timber suitable for construction takes anywhere from 25 to 75 years to reach the right age. That means a tree planted today won't be ready to use until your grandchildren are grown adults. The world can't wait that long. Cities are growing faster than forests can recover. That's exactly why builders have increasingly turned to steel and concrete. These materials are produced quickly and can handle enormous loads. But that speed comes at a cost. Steel and concrete production together account for a significant share of all the carbon dioxide humanity releases into the atmosphere every year. That's the trap. Wood is slow but clean. Steel and concrete are fast but devastating for the climate. For a long time, it seemed like there was simply no third option, either slow and clean or fast and dirty. But one material had been quietly waiting for its moment for nearly 40 years. And that material is bamboo. The first thing you need to understand is that bamboo is not a tree. It's grass. The same plant family as the long grass in your backyard, just incomparably larger. And on paper, bamboo looks almost too good to be true. It's the fastest growing plant on Earth. Some species add more than a meter per day, meaning you can literally watch it grow in real time. Bamboo reaches full maturity and strength in 6 to 9 years, while trees need decades. There's one more important detail. Because bamboo is a grass, cutting it down doesn't mean destroying it. The roots stay alive underground, and a new shoot grows back on its own. No replanting, no bare hillsides, no long wait. Now let's talk about strength, and this is where things get really interesting. By weight-to-strength ratio, bamboo outperforms steel in tension. Its raw strength is more than double that of ordinary timber. In Asia, this has been known for millennia. Bamboo was used to build homes, bridges, and scaffolding long before modern engineering existed. In some cities, construction workers still climbed bamboo scaffolding on skyscrapers and trust it with their lives. So why, if bamboo is so fast, strong, and eco-friendly, didn't engineers start building serious structures with it decades ago? The answer is straightforward. A natural bamboo culm is a headache for any builder. First, it's hollow, which makes connecting structural elements extremely difficult. Second, it's round, while builders are used to working with flat rectangular beams. Third, and most importantly, its strength is inconsistent. One culm might be incredibly strong, while another, cut from the same plant, is weak and unreliable. Drive a bolt or nail into bamboo and it splits along the grain. Without special treatment, it rots quickly and attracts insects. Now think about how construction projects actually get approved. An inspector can't walk onto a job site and say, "This beam will probably hold." Engineers need materials with predictable, reproducible properties at any temperature, under any conditions, 30 years after the building goes up. Wild, unprocessed bamboo couldn't offer that guarantee. That's exactly why the engineering world gave bamboo a nickname that stuck for nearly a century: the poor man's wood. A material for huts, not for real cities. The breakthrough didn't happen when scientists found a new species of bamboo. It happened when someone asked a completely different question. What if we stopped treating bamboo like wood? What if we treated it as a raw material, the way flour is a raw material for bread? That question led to the creation of a material called bamboo scrimber. The manufacturing process looks almost unbelievable. A whole bamboo culm isn't sawn into boards. It's fed through machines that crush and tear it apart along its natural grain. In the industry, this step is called fiberization. What comes out the other side doesn't look like lumber. It's a loose, fibrous mass that resembles coarse straw. And here's the brilliant idea. All of bamboo's weaknesses, the hollow interior, the round shape, the tendency to split, the inconsistent strength, simply disappear. Because the original culm no longer exists. It's been completely broken down into fibers. The fibers are then dried, saturated with a special resin, aligned in one direction, and pressed. And we're not talking about light compression. The fiber mats are subjected to extreme pressure while being heated simultaneously. Nearly all the air is literally squeezed out of them. What comes out of the press makes engineers stop and look twice. A dense, solid block that can be heavier than water and harder than most hardwood species available on the market today. An unpredictable wild plant has been transformed into a uniform, reliable, industrial material. And the process is nearly waste-free. About 80% of the original culm is used, including the curved and low-quality sections that used to be discarded. Here's an important fact that surprises a lot of people. This isn't a recent invention. The first high-strength version of this material was created in China back in 1987 at Nanjing Forestry University. The science has been quietly improving for nearly 40 years. What changed wasn't the chemical solution. What changed was the scale and the ambition. But a strong material alone isn't enough. For it to change the world, it has to clear the most boring but most important barrier of all: building codes and standards. Building codes change slowly on purpose. The cost of a mistake isn't money, it's human lives. An engineer can't use a new material in a school or a hospital just because one study showed promising results. It takes years of testing, agreed-upon standards, and transparent documentation. Until recently, bamboo didn't have any of that. When researchers examined companies producing structural bamboo materials around the world, they found an interesting picture. Only about a third of them published clear strength data for their products, and even fewer held basic environmental certifications. For an architect working on a real project, that's a serious problem. You can't responsibly build structures where people walk in every day on numbers nobody is willing to show you. But the gap is closing fast. Engineered bamboo is now being tested to the same international standards as structural timber. In the 10 years leading up to 2024, roughly 7,000 scientific studies on engineered bamboo were published. Each one adds the evidence that inspectors and engineers need before they sign off on a building permit. And once that confidence arrived, people started building things that nobody would have approved just 10 years ago. For a long time, the joke about bamboo buildings went like this: great as long as they are single-story and in a warm climate. A nice gazebo, a pedestrian footbridge, an eco-resort. Charming, but not serious engineering. Then everything changed. In China, the world's first 7-story building, constructed primarily from engineered bamboo, was designed and built. This isn't decorative cladding. The columns, beams, and floor systems are made from prefabricated bamboo structural elements. 7 full stories built from a plant that the construction world had dismissed as a material for huts. And they didn't stop there. An engineer who spent decades working between universities in China and the United States built vehicular bridges from engineered bamboo capable of handling real traffic loads. One of those bridges in Hunan province was assembled from prefabricated bamboo elements by a small crew of workers in about a week, with no heavy construction equipment. A bridge made of grass, carrying trucks. That's the fact that genuinely shocks people in the construction industry. Engineered bamboo is doing what was once the exclusive domain of steel and concrete, carrying real loads in real buildings where real people walk in every day. China isn't treating this as an interesting experiment. It's national policy. In 2022, the country launched a global initiative together with the International Bamboo and Rattan Organization with a simple and bold name: Bamboo as a Substitute for Plastics. The following year, a 3-year national plan was adopted for the large-scale deployment of bamboo in place of high-carbon footprint materials, steel and concrete. According to the country's own data, bamboo forests absorb and store enormous amounts of carbon every year simply through natural growth.
China controls about 1/5 of the world's bamboo supply and has built a complete industrial supply chain, from forest to finished structural beam. The technology is spreading. New companies are emerging in the United States, India, Indonesia, Vietnam, Singapore, and South America. For builders facing carbon taxes and tightening environmental regulations, a material that grows back in less than 10 years and locks carbon inside the structure isn't just a nice idea. It's a real competitive advantage. But before we paint a picture of a world built entirely out of grass, it's important to be honest about the limitations. Bamboo scrimber is bonded with resin, typically phenolic resin. That's what gives the material its strength and moisture resistance. But it means we are no longer dealing with a pure natural material. It's a composite. Questions about how it behaves in a fire, how it holds up over decades, and what happens to the resin when a building is demolished are still being studied. There's also a manufacturing barrier. Turning raw bamboo into certified structural beams requires factories, specialized equipment, and hydraulic presses. China has been building that infrastructure for decades. A country with abundant bamboo reserves but no industrial base can't simply start producing certified structural elements overnight. There's no longer a science problem. It's a problem of investment, training, and political will. But none of these limitations cancel out what the science has already proven. They simply mark the distance between what's possible today and what still needs to be built. Engineers took a plant that the construction world dismissed as a material for huts. They stopped treating it like wood, broke it down to the fiber, and pressed it back into something stronger than the timber it's meant to replace. It grows back in less than 10 years without replanting. It stores carbon instead of releasing it into the atmosphere. And right now, it's already holding up 7-story buildings and carrying trucks across bridges. For millennia, building bigger and better meant cutting down what takes a lifetime to grow. For the first time, we have a serious structural material that can grow back before a child finishes school. That's genuinely new and genuinely important. If this video changed the way you look at the next building you walk into, hit like. It really does help the channel keep going. Subscribe and turn on notifications so you don't miss the next one. And drop a comment below. If a plant that was laughed at for 100 years turned out to be this powerful, what else do you think we're overlooking right under our noses?